In previous few lectures, we have discussed in very detail the Drude-Lorentz theory and its applications. You know, Drude-Lorentz theory is also known as a free electron gas model, and it is a classical theory because in Drude model, electron is treated like a classical particle obeying the Newton's laws of motion and Maxwell-Boltzmann distribution law, which is actually a classical statistics. So, our previous discussion on Drude model and its application was purely a classical treatment. But actually, we know electron is not a classical particle. Electron is just a quantum particle, and in fact, the behavior of any system which will be determined by electron, that must be treated taking the electron as a quantum particle. It means for the correct development of theory, we must adopt the quantum mechanical approach if electrons are involved in that discussion. So, in view of this very fact, Sommerfeld provided the quantum theory of free electron theory of metals. And actually, in Sommerfeld's quantum theory, electron is treated like a quantum particle. Although, in his theory, Sommerfeld accepted the free nature of valence electron. It means when you talk about the Sommerfeld's theory, you again say that the valence electrons of a metal are free. They are almost free from any interaction, and they randomly move inside the metallic surface or a potential barrier at the metallic surface. Okay. So, accepting this free nature of valence electron but applying quantum mechanical approach, Sommerfeld developed a theory which is actually called Sommerfeld's quantum theory of this free electron theory of metals. Okay. So, you can say that considering the free nature of valence electrons as assumed in classical theory, Sommerfeld treated the problem quantum mechanically using the Fermi-Dirac statistics rather than the classical Maxwell-Boltzmann statistics. Okay? In fact, in this theory, the possible electronic energy states in the potential energy box and the distribution of electrons in these states are determined using quantum statistics instead of the classical statistics. Okay? And in this regard, we will see the problem of one-dimensional and three-dimensional cases of an electron of electron. Okay? So, in this lecture, our aim is to discuss the free electron gas in a one-dimensional box. Actually, this problem you have already studied in your course on quantum mechanics. And you can see my playlist on quantum mechanics, and there you will find particle in a potential box, in a one-dimensional potential box. The same problem has been treated, but in that case you will find the calculation of the energy eigenvalue, the eigenfunction, okay, all these things you will find there and discussion on that. Here actually our aim is to find the important quantities like Fermi energy, like total energy, like density of states. On the basis of this free electron gas in one-dimensional potential box. Okay. So first of all, see the basic theory of free electron gas in one-dimensional potential box, which I have already discussed in the my lecture on quantum mechanics. But here I am just repeating the same thing. Okay. So let us see in this see this figure. We consider here an electron of mass m, and this electron is bound to move in a one-dimensional crystal of length L. Actually here, let us say this is point O and this is point P, and this OP is equal to L, and this represents the length of a one-dimensional crystal. Okay, and we assume that inside this crystal there is an electron whose mass is m, and it is confined to move freely inside this crystal. But how you can say that this will be confined to it? Actually, it is assumed that the electron is prevented from leaving the crystal by the presence of a large potential barrier at its surfaces. You can see at point O, the potential function is infinity, and at point P also this potential function is again infinity. So this is just an infinite potential barrier, and that's why we can say that this electron cannot escape through these potential barriers. So we simply assume in this Sommerfeld's theory that at the surfaces of a crystal the potential barrier height is infinite, and so no electron can escape through the surface. Okay, we assume it. But inside the surface, the electron moves freely without any interaction, and so its potential energy V has been taken 0 inside the metal surface. Okay. Although the barriers extend for over a few atomic layers near the surface, these are taken infinitely large for the sake of simplicity. Okay. Why we have taken this potential barrier height infinity, you can see this is just for sake of simplicity, but in practice this potential barrier height will be in fact a few atomic layers near the surface. Okay. In fact, this problem, as I have told you earlier, is just identical to that of an electron moving in one-dimensional potential box, and this one-dimensional potential box has been represented by this line OP in this figure. You can see. Okay. Now, the potential energy function V of x, how it varies here with x, you can see. In fact, this potential energy function V of x, you can see, is 0 everywhere inside the potential barrier, that is inside the surface of this specimen. And so I have mentioned it here that this V of x is equal to 0 when 0 is less than x and this is less than L. You can see if the electron is lying between this point O and this point P, then x will be lying between x0 and L, and in this region actually this potential energy function is 0. But if you talk about a region for which x is less than 0, in this region actually x is less than 0, and see this region after x equal to L, here x is greater than L. Actually in these two regions, that is region number 1 and this region number 2, actually there will be no probability of finding of electron, and here actually potential function is infinite. Okay. So you can say that this V of x is infinity for x less or equal to 0 or x less or equal to L. Okay. Now our aim is to deal with the physics of this metal by taking the free electron as the agent which will determine all the properties of the metal. And now in Sommerfeld's theory you are treating the electron as a quantum particle. And if we want to solve any problem or discuss any problem in quantum mechanics by Schrodinger's wave mechanics, then definitely everything is discussed in terms of the wave function of the particle. Okay? Since here electron will remain in different energy states, and corresponding to the different energy state, probably the wave function will be different. We can hope, we can assume. So for our calculation, let us consider that this psi n is the wave function of the electron found in its nth state. That is, when the electron is in its nth energy state, then the wave function associated with it is psi n. Here the subscript n actually represents the nth energy state. Okay? Now, to handle this problem quantum mechanically, first of all we have to write down the equation of motion of this electron. But in this case, since the problem is now treated as a quantum mechanical problem, so we cannot write the equation of motion in terms of Newtonian mechanics, but you have to think about wave mechanics, or you have to set up the Schrodinger time independent equation for this electron. And in one dimension, Schrodinger's time independent equation is given like this. This is d2 psi n by dx square plus 2m over h bar square times En minus V of x psi n equal to 0. In this expression, actually this En represents the total energy of the electron. This is total energy. And V of x, this is energy of interaction, that is potential energy. And the quantum physicists call the potential energy simply potential. Actually, whenever the word potential is used in quantum mechanics, that refers potential energy market. So here you can say that this V of x is the potential or potential energy of our electron. Now, if your aim is to write down this equation in the region between x equal to 0 and x equal to L, where electron is present, actually beyond this region electron is not present. As you have seen, since at the surface of the metal the potential barrier height is infinite, so electron is actually confined to move inside this potential barrier. And there is no probability of finding of electron outside of it. So we will talk about only the region where electron is present, and that very region is the region lying between x equal to 0 and x equal to L. But in this region, you have seen that the potential energy function is 0. And so the Schrodinger equation in this particular region will be what? That will be obtained simply putting this Vx equal to 0. So the Schrodinger equation in the region where actually 0 is less than x and this is less than L, in that very region, Schrodinger's time independent equation is like this. This is d2 psi n by dx square plus 2m En over h bar square psi n equal to 0. And let us put k square at the place of this 2me En over h bar square. Okay. That is, we have considered here that this k is equal to plus a square root of 2m En over h bar square. Actually, this k is a positive constant. And what is its value? You can see it here. Okay? This is actually a very important result too. You will see later on when we will talk about the energy eigenvalue of our electron, then we will use this very equation 3. Okay. Now you can see the form of this second order differential equation. This is a well known differential equation of second order of mathematical physics, and this equation has an oscillatory solution. Here psi n will oscillate in fact with x. So the well known general solution of this equation number 2 you can write like this: psi n of x equal to a sine kx plus b cos kx. Here actually these a and b are arbitrary constants. This is a differential equation or ordinary differential equation with constant coefficient of second order. So there must be two integration constant in its solution. So actually these a and b are what? These are the integration constants. Okay. And in any problem, the integration constants or these arbitrary constants are obtained by using the proper boundary conditions. Here we have to find the values of two arbitrary constants a and b, so there must be two boundary conditions. As you have seen, I have told you earlier that at the boundaries, that is at x equal to 0 and x equal to L, okay, the potential function is infinite. So beyond this region between 0 and L, there is no probability of finding of electron. And if probability of finding of electron is 0, then according to max probability distribution of wave function, modulus of psi n of x square, that will be equal to 0. This is probability density in those two regions. Okay. So you can write the boundary condition in this manner, that psi n will be 0 when x is 0. So at the place of x here I have written 0, and you can say the first boundary condition is psi n at x equal to 0 is 0. And again in the region x equal to L or greater than L, there will be no probability of finding of electron. And so in this region too, electron will be not present, and therefore the wave function in that region will vanish, and so psi n of L is also equal to 0. Okay. In fact, these conditions are based on the fact that at x equal to 0 and x equal to n, x equal to L, this v tends to infinity. You have seen. And the product of Vx and psi n of x, this product, in this equation where you have written this equation psi n times Vx, actually this will also approach to infinity. Okay. And so in order that the wave function psi n x must be continuous, continuity is an essential feature of wave function. So for its continuity at the boundary, the kinetic energy En or the total energy En must also become infinite. Okay? But that is not feasible, that is not possible. And that's why we simply say that this psi n of x at x equal to 0 is 0, and psi n of x at x equal to L is also 0. So I think we have clearly understand why these two boundary conditions we can use. Now applying these two boundary conditions on our resulting equation 3, we will be able to find the values of A and B. Okay? A and B. So now let us first of all apply the first boundary condition, that is psi n at x equal to 0 is equal to 0 on this equation 3. And for this what you will do? We will simply take x equal to 0 in both of the terms in RHS. And then you can see psi n at x equal to 0 is 0. So in LHS there will be also 0. And therefore, after applying the first boundary condition, our result is 0 equal to a sine 0 plus b cos 0. Okay? But sine 0 is 0. So the first term in RHS is 0. But cos 0 is 1. So here the second term is only b. So you can see the arbitrary constant b is in fact 0. B is 0. And if b is 0, then the resulting eigenfunction or the resulting solution of this equation 2 will be simply equal to psi n of x equal to a sine kx. A sine kx. So I have written it here. This is psi n of x equal to a sine kx. Okay. Now we will impose the second boundary condition. What is the second boundary condition? You know, psi n of x is equal to 0 at x equal to L. Let us impose this condition on this equation 4. So at the place of x now you will write L, and at the place of psi n of x then we will write 0. So 0 is equal to a times sine kl. And so you can say that sine kl is equal to 0. But if sine theta is 0, what is the general value of theta? General value of theta will be n pi, because sine n pi is equal to 0. Okay? And if sine kl is equal to sine n pi, then kl is equal to n pi, and k is what? This k is equal to n pi over l. But what is this n? N is actually the quantum number, and its values are 1, 2, 3, 4, 5, 6 and so on. But mark one thing here which is very important, that when you say that sine theta is equal to 0, then theta is equal to n pi, and we take in mathematics n equal to 0, 1, 2, 3 and so on. But here n equal to 0 is restricted. Mathematically it is alright, but here in this present problem you can't take this quantum number n equal to 0. Why we cannot take n equal to 0? You can see, if we will take n equal to 0, then k will be 0. And if k is 0, then for all values of x, whatever the value of x is, sine kx will be 0, and so psi n of x will be equal to 0 for all x. For all x. But is it physically possible? Answer is no. You know, for x lying between 0 and L, psi x cannot be 0, because in this region electron is present, and if electron is present, the probability density of finding of electron will be not 0, and so the wave function cannot be 0. So you can say that for all values of x, since psi n of x cannot be 0, that's why we cannot take n equal to 0. So physically it is not possible. Although mathematically it is alright, but physically you can't take n equal to 0 in present situation, because I have told you, if you will take n equal to 0, then k will be 0, and if k is 0, then for all values of x, sine kx will be 0, and our wave function will be 0, which is unphysical. Okay? That's why we take the values of this quantum number n as 1, 2, 3 and so on. Okay? These are its values. Okay? Now we will substitute this value of k which we have obtained here in this equation 5 in equation 4. And so the allowed wave function or the valid wave function for this electron is given like this. This is psi n of x equal to a sine n pi over L into x. Okay. But in this equation 2, this a is not known till now. You have not what is the actual value of a, you don't know. This a is actually called normalization factor or normalization constant. So applying the normalization condition, taking the wave function psi n of x equal to this much defined in equation 6, we will obtain the proper value of a sometime later. But before that, we are talking about the energy eigenvalues of this electron. What are the energies of this electron? Now we will see. As I've told you earlier, see this equation number 3. In this equation, don't write this 3 because here I have written this equation 3. So see this result. K equal to 2men divided by h bar square root. But we have obtained now the value of k. So from this result we can easily find the energy eigenvalues En. And for this, let us square this k. You can see k square will be equal to 2men over h bar square. And so from that result we can write k square is equal to 2men over h bar square. Okay. But you have seen that this k is equal to this much. This is n pi over L. So n square pi square over L square, that is equal to 2men over h bar square. And from here you can easily see that this energy eigenvalue En is equal to n square pi square h bar square over 2ml square. Okay. So this equation A1 represents the energy eigenvalues of our electron inside this metallic surface. Now, first of all, we will obtain the actual or proper value of this normalization constant A, and then we will discuss the results for the energy eigenvalue and the eigenfunction or wave function jointly later on. Okay. So now let us apply the normalization condition. You know, normalization condition says that integral psi of x mod square dx for all space, that is from minus infinity to plus infinity, this is equal to 1. If psi of x is a normalized eigenfunction, then this integral must be equal to 1. This very condition you have definitely studied in your course on quantum mechanics. This is called normalization condition. Okay. Here all space means what? All space means the space where our system is lying. Here you can see the electron is confined to move between x equal to 0 and x equal to L. It is never outside of this region. So for this electron, the region between x equal to 0 and x equal to L is all space. And so corresponding to this minus infinity here in this proper problem, you have to write x equal to 0. And at the place of plus infinity, you will have to write L. Okay? Mark it. Now you can see mod of psi n of x square. What will be this? This is simply equal to conjugate of psi n of x times psi n of x dx integral. But as you can see, the wave function psi n of x obtained here, you can see it is real, not complex. So its complex conjugate psi n star of x will be also equal to a sine n pi x over n. So substituting the values of this psi n star and psi n here, our result will be a square times integral 0 to L sine square n pi x over L dx equal to 1. Now you know sine square theta, this is 1 minus cos 2 theta divided by 2. Here at the place of theta there is what? There is n pi x over L. So this will be equal to actually a square over 2 integral 0 to L 1 minus cos 2n pi x over L. And this is equal to 1. Now, you can impose this integral on both terms separately inside this square bracket. So this will be a square over 2 integral 0 to L dx minus a square over 2 integral 0 to L cos 2 pi and 2n pi x over L dx, and that is equal to 1. Now, it is a very simple integral. You can integrate this function, and when you will integrate this second term, you will see after substituting the limit that this integral vanishes, its value is 0. And the integral of dx will be x, and after substituting limit, that will be L minus 0, that is L. And so, the value of this integral is a square over 2 into L, and that is equal to 1. And that's why you can say that a is equal to a square root of 2L, 2 by L. So this is the value of normalization constant or normalization factor. Now substituting this value of a, that is normalization factor, in the wave function defined in this equation 6, you will get the normalized eigenfunction or the normalized wave function. So the normalized eigenfunction is given as psi n of x equal to a square root of 2 by L sine n pi x over L. Okay, this is the normalized eigenfunction. Now in this equation A2 we have derived the expression for normalized wave function, and in equation A1 we have the energy eigenvalue of this electron. Okay, actually on the basis of these two results, all properties of metals will be discussed in the forthcoming lecture. Okay, but here we will see a brief discussion on these two results. Let us see. You have seen that the energy eigenvalue is given as En equal to n square pi square h bar square over 2ml square. You can see. Since n has discrete values, which is 1, 2, 3 and so on, so definitely the energy eigenvalue spectrum of this electron will be a discrete spectrum. Energy of the electron is not continuous. It has discrete values, and those values can be obtained by substituting the values of n. So when you will take the lowest value of n, which is 1, you have seen that we can't take n equal to 0. So n equal to 1 is the lowest or least value of n. And so this energy E1 is the least energy of the electron inside this metal surface. And that will be equal to what? Take n equal to 1, then E1 will be equal to pi square h bar square over 2ml square. This is the lowest energy eigenvalue of electron in this metal. Okay. And what is the wave function when n is 1? You can see this expression A2. Taking n equal to 1, the wave function is psi 1 of x equal to a square root of 2 over L sine pi x over L. So corresponding to this energy eigenvalue, you can see there is one and only one eigenfunction. Only one eigenfunction. So can you say that this energy level E1 is degenerate or non-degenerate? Answer will be non-degenerate. You have learnt in your course on quantum mechanics. Because this energy eigenvalue corresponds only one eigenfunction. It means electron is found in only one state, quantum state. And so this energy eigenvalue is non-degenerate. Okay? Similarly, when you will take n equal to 2, what will be the energy? E2 will be equal to, you can see, 2 square means 4. This is 4 pi square h bar square over 2 ml square. Okay? But you have seen that pi square h bar square over 2 ml square is E1. So when n is equal to 2, then the energy of our electron is 4 times of E. That is 4 times of lowest energy. So you can see between E1 and E2, there is no energy eigenstate of the electron. The least energy of electron can be equal to E1, and after that its energy will be 4E1. All the energy eigenvalues lying between E1 and 4E1 are prohibited. They are not the allowed energy eigenvalues. And that's why we simply say that the energy eigenvalue of this electron inside a particle in one-dimensional box is quantized. You know, if a quantity has discrete values or the values of a quantity are governed by integer rule, then such quantity is called quantized quantity. So energy of this electron is also quantized. Now if you take n equal to 3, you will get the third energy eigenvalue, and that will be equal to 9 pi square h bar square over 2 ml square. And so this will be equal to 9E1. So you can see energy is E1, then it is 4E1, then it is 9E1, and then it will be 16E1, and so on. Now you can also see that the separation between two successive energy levels, if you want to find it, then you will find 4E1 minus E1, that will be equal to 3E1. It means the energy gap between the first energy level for n equal to 1 and for the second energy level, that is the excited energy level, first excited energy level, is equal to 3E1. But what is the difference of these two energies for the energy level n equal to 2 and n equal to 3? You can see for n equal to 3, the energy is 4,9E1, and for n equal to 2, it is 4E1, and so this will be 5E1. So the different energy levels in this case are not equally spaced. As the value of the quantum number n increases, the energy levels are more and more separated. More and more separated. This is just opposite to the idea in Bohr's theory. When you talk about an electron of hydrogen or hydrogen-like atom, then it is found that with increase in n, the energy levels becomes closer. But here in this case, the energy levels do not come closer, but they move apart from one another. So the separation between the two successive energy levels is increasing on increasing the value of n. Okay. But one thing here is very remarkable, that the allowed energy eigenfunction psi n of x and the allowed energy eigenvalue En exist only for integral values of n, and so they have quantized value. Actually, the number n, as I have told you, is called a quantum number, okay, and hence energy spectrum consists of discrete energy levels where the spacing between the levels is determined by the value of n and l. This n and l determine the energy spacing between two energy levels. In fact, it is found that this spacing between two energy levels decreases with increase in L. As the value of L will increase, the separation between two energy levels decreases. This is the separation. Let us say this is the separation delta E. This separation will decrease when L increases. So if you consider that this L is of the order of centimeter, then it is seen that this difference in the energy between two levels tends towards zero. It means the energy level become continuous, and that is the classical case. But if we are talking about the value of L in atomic dimension, so if L is in atomic dimension, then the separation or the energy gap between two energy levels has an appreciable value. You can't neglect it, and you have then to say that the energy eigenvalues of the particle inside a one-dimensional potential box is quantized. Okay? So it is very remarkable that L is large. A large just does not mean say it is in the order of meter. Even L is of the order of centimeter. Let us say 1 centimeter, 2 centimeter, 3 centimeter, or you can say few centimeter. Then the energy levels becomes continuous. You cannot talk about the separated or the discrete energy levels, but like this a continuum of energy level is formed. Okay? Or you can say that this energy difference between two successive energy levels tends towards zero. But when L is small means it is of the order of atomic dimensions. It means what is the size of atom? You know, it is very small. So L is if of that order, then the energy levels are not continuous but discrete. So this quantum mechanical idea will prevail, will exist when you will talk about a potential box having length of the order of few atomic dimensions. Okay? So this is the basic theory of an electron in a potential, one-dimensional potential box. But actually, what we have learnt in this lecture, that is not very important in case of solid-state physics. This is the problem of quantum mechanics. But after this discussion, our aim will be actually to discuss the properties of the metal or the free electron present in the metal using the results obtained in this lecture. And in this regard, you will see the calculation of Fermi energy, the calculation of total energy, and the density of states. And that is the subject matter of our forthcoming lecture. Okay? So I think you have definitely enjoyed this video, and if you have enjoyed, write down these things in your notebook as always I told to you, because that will be a very good note for your examination purpose. Okay? Thank you very much.